Hey, so recently I've been working on a little project in the world of game development, and I thought the results were pretty interesting, and I figured I'd share it with anyone who was interested. So in the world of game development, we have these game engines, which are a tool that you can use, which try to streamline a lot of game development and take care of a lot of things that are common to many games. So for example, they'll help you deal with your physics and lighting, animation, audio, handling the user input, and also helping you launch to multiple platforms. So you can develop your game once, and with hopefully minimal changes, you can have that same game run on Windows and Xbox or what have you. Uh, but there's a common question that comes up in game development, very common question, which is, do I really need a game engine, or can I just build this game myself? And the classic answer to this is, yeah, you can build it yourself. You'll get better performance and you have more control over your project, but it's usually not worth the extra effort. And that sounds pretty reasonable, right? Like I just listed off a whole bunch of features that the game engine kind of takes care of for you. But I wanted to dig into this a little bit more, like this better performance and this extra effort. How extreme are those really? How much more effort is it, and how much performance difference can we really expect? Um, so I'm not trying to give the definitive answer to this, but I'm just trying to get some numbers, at least something to gauge off. So the game engine I'm going to be looking at is Unity, which is one of the most popular game engines in the market, if not the most popular game. A huge number of games have been built on it, both indie and AAA. So it's very battle tested. It's a well proven game engine. And recently, the folks working at Unity Technologies have been making a big push for performance with this data oriented tech stack. Uh, which the short story is basically they're moving away from the sort of object-oriented style of development where your data is kind of hidden as implementation details behind layers of abstraction, oftentimes times many layers of abstraction. And data-oriented style of coding is basically trying to remove a lot of those layers and just directly thinking, okay, what is my data and how is it changing every frame or every time step or what have you. And so there are three components to dots. The first, which is kind of the most obvious one people think of, and sometimes they use the terms interchangeably, is the entity component system, or ECS, which is kind of how the framework within which you develop your code in this data-oriented style. There's also the Burst compiler, which is a new compiler they're developing, which plays nice with the kind of data-oriented style of writing code, the way you do memory allocations, things like that, and the job system to help run your code on multiple cores and really leverage the full CPU. And so Dots is technically still in preview. They have been encouraging developers use it for quite a while though, so they must have at least a reasonable amount of faith in it. And it is planned for full release very soon, early next year. And so they've released a sample project publicly available. It's just on GitHub to kind of demo Dots to show how you might actually implement some of the stuff in practice. And it also provides some motivation for why we should even care about implementing our project with Dots in Unity. So let's take a look at that now. So here we are in Unity looking at the Dots or data-oriented tech stack sample project. And you can actually configure it to use Dots or the ECS system. You can toggle that on and off. We'll leave it off for now, and we'll just show you the general gist of the game. So you play as this dude down here, and you just run around this large sort of flat surface, and these little wiggly monster dudes will start spawning randomly, and they will just chase after you. So as you move around, they'll track after you. And then you've got this gun, which every shot shoots this like grid of bullets, and the number of bullets that you fire with every shot is controlled by this spread amount over on the right here. So currently it's set to 10, which means that we'll fire that number squared. So it'll shoot 10 by 10 grid of bullets. So you end up with 100 bullets per shot. And we got a max firing rate as well of 0.1. So that's we can fire once every 0.1 seconds or 100 milliseconds. So that would be if we were to hold the button down, that's how fast we can fire. So we're still not using ECS, but let's just see what happens when we increase this number. So remember that's squared, so we just went from 100 bullets per shot up to 400 bullets per shot. And let's see what happens when we do this. And you'll see that the game pretty much just lags out completely and is pretty much unplayable if you just try to even shoot once. And if you hold it down, it's terrible. So pretty much unplayable in that state. ECS to the rescue. So we'll just use this little toggle here, and it's not really anything too magical. So we'll just take a look at my fancy IDE. That just toggles this boolean here from false to true, and it just sends you down different code paths. So it'll just spawn bullets using this entity component system, which you can grab the code yourself from GitHub, but basically it just uses this new system. And we also have to do that for the enemies so they collide with each other properly. And so remember, at 20 bullets we were completely lagging out, but now we've turned on ECS and gone down that code path. And if we take a look, you'll see that its performance is just fine. It's running pretty smoothly, no worries at all. And we can even increase the spread amount, probably not that much, 50, so we're at 2,500 bullets per shot. And it still performs pretty well. And also remember, we're in the Unity editor at the moment, so this is not an optimized release build of the game. But we can still see, it's doing pretty well. Now, while the gameplay of this project is actually pretty simple, there's actually quite a few subtleties going on here which are easy to overlook. So for example, we've got things like the shadow of the player character and the shadow of the monsters that are wiggling around. We also have the lighting from these bullets, so you'll see that the player actually glows. So we've got this muzzle flash when he shoots, and that lights up the whole character and some of the floor. We've also got this bloom effect, so you can see, it's easy to see from his back. He's got this backpack with lights on it, and you can see the lighting kind of, oh, that was close, actually bleeds out from the backpack. This kind of, it's called bloom. You can call it emissions or whatever you like. And we also have animations. So as the character moves around, he has different animations for different directions, but it'll also merge between them. So if you run forward to the left, he'll go like this. They're actually a little bit dodgy, so if you run forward to the right, it's pretty weird, but an attempt was made. There's also this camera smoothing kind of effect. So you'll notice the camera doesn't stick to the player super strictly. It'll kind of transition between locations and kind of almost rotate around a bit. Okay, so here's the plan. I'm going to build a clone of that dots sample project, and I'm going to build it from the ground up. So I'm not going to use Unity or any other game engine. I'm just going to start with a blank code base and just make the game, so to speak. And I'm going to try to get the gameplay experience as similar as possible. So I'm not just going to stop with the actual game mechanics. I'm going to try to get all the lighting and shadows, animation, sound. I'm going to try to get everything there. I'm going to use the same constraints as the dots one. Like when they were demoing it at their conference, they mentioned they sort of placed this restriction on themselves not to use object pooling for the bullets. So I'll stick with that constraint. Also, I won't worry about being frame rate independent because their version isn't, and I'll just do discrete collisions. I'm going to be building it in C++. I'm going to keep the dependencies to a minimum, so I'm going to use OpenGL and a window management library. some libraries for dealing with file formats because I don't want to have to deal with that stuff, and some matrix math libraries. And after all this is done, we'll compare the performance of these two projects and also try to get an estimate of the amount of effort required for each of these. So I am going to build this now, and I'll see you all soon.
Several days later.
Here we are in the hand-built clone of the sample project, and it's reasonably complete. So we got the general gist of the game, the guy running around, wiggly little monsters chase after you, shoot a bunch of bullets at them. So we've also got a lot of those subtleties we're talking about, like the shadows, which I think are actually a bit better in this version. And we've got the lighting, so you can see the bloom or emission effect from his backpack there and the other light areas. And the animation, so you can see he blends between all the different angles he can be running at. There are a couple shortcuts I took. I was just kind of running out of time. So the muzzle flash there, that is it's not an actual particle system. I just took some screenshots basically of the particle system used in Unity, and I'm just using a sprite sheet to display that. Also, I haven't got the camera smoothing. We just follow him pretty strictly there. But I don't think those things are going to impact the performance measurements too much, and we'll have to make sure we account for them when we're doing the effort estimations though. So I was messing around with the hand-built version of the sample project, playing with the numbers a bit, and I decided to be a bit silly, and I set the bullets per shot to 50, or the spread amount, so 2,500 bullets per shot. But I set the firing rate to 0. So basically you can just fire every single frame. And you can see this here. And it still performs very well. So we're not really dropping frame rate at all here. So yeah, it works pretty well. We'll do proper performance analysis, of course. I'm just mucking around. Okay, so let's just clarify how exactly we're going to do these comparisons. So I'm going to have 4 enemies spread evenly around the player. And the reason I want to have enemies in there is so that the collision detection algorithms can run and the performance of those can be included. And so the enemies will never die, just to make sure they're always there in every frame in all the tests. I'm going to get the character to shoot in the consistent direction in all the tests. And we're going to stick with that fire interval of 0.1 seconds in between the shots, or 100 milliseconds. And I'm going to gradually increase that spread amount variable, measuring the performance each time I do that. And then I'm going to stop once the time to process a single frame is equal to that firing interval. So we're not frame rate independent at all, so we can't actually fire bullets faster than our frame rate allows. And so if you're curious about the hardware that I'm running this on, you can have a look. Okay, so what are we actually going to be measuring? So we're going to start off with frame time, which is basically the amount of time elapsed in between each frame. So it's the inverse of frame rate, which is a pretty common metric to use. You might hear the term 60 FPS or 144 FPS or something like that. But we're just going to use frame time. It's a bit simpler, and it kind of matches up better with the other metrics, being consistent with lower is better. And we're also going to look at the resource usage, so the usual assortment of RAM, CPU, and GPU. And I'm just going to use the Windows Task Manager for this. It's much easier to look at this on a per process basis without other applications kind of interfering with things. And I would like to look at startup time, but unfortunately I don't have the license necessary to get rid of the splash screen on a Unity release build, so I'm just not going to look at startup time. I'm also going to close pretty much all other applications while I'm performing these tests, so I'm not going to be recording any of it. So I'll see you afterwards.
A few moments later.
Okay, the results are in. And we're going to start off by looking at the frame time. So this is the amount of time it takes us to process every frame in the game. And again, we're going to be averaging over 100 frames. And so lower is better. 7 milliseconds is the limitation of the hardware that I'm using. So it corresponds to around 144 frames per second. And another interesting value to keep in mind is 16 milliseconds, which corresponds to 60 frames per second, which is a very common setup to have. And it feels very smooth at 60 frames per second. Hardcore gamers probably won't like it, but for most people, that feels pretty good. So, data. Um, as you can see, we've got 4 rows here. So the first row is the spread amount. That was the variable we were playing around with in the Unity editor, and I've cloned this variable in the hand-built version of the project. And the second row, it's simply just the square of that number. So it's the actual number of bullets we fire every shot. And here we have the frame time of the 2 different implementations, this average value over 100 frames. And we won't go too much into this table form, we'll look at a graph soon, but as you can see, when the number of entities or bullets is pretty low, they're both able to max out the frame rate in my setup. We hit that threshold of 104 milliseconds, which is really long. It's not playable at all. Even 72 is probably not very playable. 27, some people might be okay with it. A bunch of people will rage quit. But you can see we hit that limit at around 44,000 bullets per shot. And the hand-built solution is still purring along pretty nicely there at that number of bullets per shot, and at around 420,000 bullets per shot, the hand-built engine kind of fails. So if we look in the graph form, we can see that difference here. So they start off very similar, and the more extreme you go, the bigger the difference is, with around a 10x difference up here. But in these realms that you're probably more likely to care about, it's more of a 4 to 5 times the difference. So CPU utilization, this is not too interesting. So we'll just go straight to the graph. You can see the hand-built version is pretty steady in the mid 30s, whereas the Unity version starts off low, then kind of spikes up and has this steep drop. And we'll see this that steep slope downwards kind of mirrored in the GPU utilization, where it pretty much just falls off a cliff, and it's borderline idle when we're at that limit of frame time. And I think this is a pretty strong indication that the Unity version is not at all bound by GPU or CPU usage. I suspect it's probably something to do with I/O between main memory and the GPU memory. So now we're at the final performance metric, which is RAM, or memory usage. And I hope you like numbers, because there you go. So again, we've got the same first 2 rows of this spread amount variable, and then the square of that number for the actual number of bullets per shot. And you'll see there's a fairly stark difference between the RAM used by the Unity implementation compared with the hand-built. And it's actually a pretty constant ratio between the two, of around 11 or 12% of the RAM usage for the hand-built one. And if we take a look on a graph, you can see that, yeah, the Unity one starts a lot higher, and the slope is much steeper too. So it's around extra 500 bytes of RAM used for each bullet we add. That doesn't necessarily mean all those bytes are for the bullet itself. Could be various adjacent and related data structures, but the application uses 500 bytes more memory per bullet, and the hand-built one uses around 40, which makes sense because that's exactly what I'm storing. In terms of where these 500 bytes come from, I did a little bit of investigation, and looking at a single entity bullet and the entity debugger, you can see a smorgasbord of data stored here, a bit of duplication. But if we assume some data types, that's around 200 bytes per bullet, which still leaves a bunch left, but I imagine it's something to do with, again, adjacent data structures, or maybe storing some KD tree of all the entities, so you can clip them more easily when it comes to render, things like that. And the memory profiler didn't provide too much insight into this either. The C# runtime is probably also a contributing factor here. Maybe there's some GC references or some bunch of data being passed to the JIT or something like that. To summarize all these performance comparisons, so the frame time of the hand-built version ranged from no difference up to a 10x improvements in the most extreme conditions when compared to the Unity version. CPU and GPU utilization was about equal when the applications were running smoothly, and memory usage of the Unity version was about 9 times that of the hand-built version. All right, so time to look at the other side of the equation. How much more work is it to build this application from the ground up instead of using a game engine, Unity in this case? So we want to get a ratio. Is it twice as much effort, 10 times as much effort, something like that. And so we're going to use this little formula here. We got E for effort, and the little subscript HB is for hand-built, and subscript Unity is for the Unity version. And so we take the ratio of these two, we can see how much more effort it is. And I didn't make the Unity version, so some assumptions will be needed, but we'll do the best we can. And so to calculate the effort ratio, we'll need a unit of measurement. And we'll need to use the same unit for both of them. Doesn't really matter too much what it is, but we just have to make sure it's the same. So for convenience, I'm going to use my unit of measurement as the effort required for the average line of C# code in the Unity project. Okay, so these are the formulas I came up with. For Unity, we start out with the number of C# lines in the Unity project. However, not all of the behavior of the Unity project is defined in the C# code. There's a lot of stuff that gets defined outside this, dealing with materials and animation graphs and lighting and scene layout, all that stuff, and that's not captured here. So that's why we got this second little factor here in brackets, which is basically how much of the total effort is relative to the coding effort. So if it's twice as much effort to get the whole thing done, then this will be a factor of 2. And for the hand-built, we started out with the number of lines in the hand-built project. Now, the effort required for one of these lines is not necessarily equal to the average line of C# code in the Unity project. So we got this little factor here to try and bring those into line. And this last one here is just to account for the fact that there are a couple of little things missing in the hand-built version. So we need to account for that. So for Unity, just a reminder, there's our equation. Let's try and find the values to these variables. So the number of lines in the Unity project was 542. So this is, if you ignore all the blank lines and comments, and I removed all the non-ECS code paths, and I changed the code style to match that of the hand-built. So I just put all the curly braces up, things like that. And this other factor of the total effort relative to the coding effort, I put that as 2. So there are a lot of elements to defining your Unity project that are outside the code. And from my personal experience, I've never worked on large-scale Unity projects, just little small toy projects. The thing we're looking at happens to be a small toy project, so that probably maps pretty well. And I did find that, generally about half the time was in the code and the other half was in the non-code stuff. So that brings our Unity effort value up to 1084. Now for the hand-built version, again, this was our formula, and the number of lines in the project was 2619, and similarly, get rid of all that stuff. And this includes everything. So C++, the GLSL, which is the shader language for OpenGL for writing code on the GPU, that runs on the GPU, and the build configuration as well. So everything is in there. The line effort ratio. Now, originally I was going to have a much higher number for this, something like around 2. because there's some complicated math you end up having to do when you're kind of, doing the ray tracing yourself, or when you're trying to figure out where the guy is aiming based on your mouse coordinates, things like that. Um, but then I looked at the Unity code, and the ECS stuff is actually it's non-trivial. And a lot of the complicated math that you end up doing in the hand-built version, that's spread over many lines anyway, so it's picked up there pretty well. The reason I did give it a bit of a boost, though, is because debugging OpenGL and the C++ code related to the OpenGL and GLSL is pretty troublesome to debug. I've often found myself just rendering pixels of particular colors to try and figure out what the state was in the GLSL code, which it does slow down development a bit. And completion, it was most there, but there was a few things missing. So I gave myself 90% completion. So we end up with an effort value of 3,638. All right, so let's put it all together. So the relative effort of the hand-built versus the Unity, with these numbers, it works out to be 3.4. So get rid of some of that false precision, and we're left with 3 to 4 times the effort of building the hand-built version of this particular game compared with the Unity version. And intuitively, that seems about right, yeah? So like a skilled Unity developer could probably get the project done in a day. And someone building it by hand, if they're sort of familiar with all the math and they're comfortable with that and they're comfortable with C++, they could probably get this working in a week with a bit of time to spare. In conclusion, the hand-built solution for this game provides strictly better performance for the measurements that we did, with a very significant difference for the memory usage and potentially significant difference for the frame rate or frame time. The difference in amount of work required was also very significant, and most of the time building the hand-built version was spent on those polished features, getting that lighting and shadows and bloom and animation blending, getting all that stuff working just right. That's where most of the effort went. Getting the actual game mechanics working and getting it all optimized, that was actually pretty straightforward. And I think it's important just to give out a reminder that this is not a one-size-fits-all comparison. For different projects, different teams, all these different variables are going to change this hugely. So I'm just giving a single data point here. And so be wary of extrapolating from that too much. All right, so that's it. Thank you for watching. I will be keeping an eye on the comment section of this video, so if you have any thoughts or questions, feel free to post them.